Hi everybody, welcome back to one of the most important lectures in all of Calculus 1. So for those of you who are going to be going on to Calculus 2, this set of material is extremely important. What we're going to learn today is a technique that you will see over and over and over again in almost every problem throughout the rest of Calculus 2. So this is a huge, big deal. And sometimes this gets lost because it happens at the very end of Calculus 1, and sometimes if we go straight through our textbook, it happens at the very, very end, at the very last thing of Calculus 1, which means it has a tendency to get overlooked sometimes, and students don't always realize that this is a huge, big deal. So when we talk about finding antiderivatives, we're really starting with something that's been horribly differentiated and reconstructing the function that it came from. So we can use things like the power rule, right? That if we have something like 2x, we know they had to have come from an x squared, right? That's undoing the power rule. Or there's other rules too, like if we have 1 over x, we know that had to have come from log of absolute value of x, right? So that's one thing we can undo. Substitution is all about undoing the chain rule. So let's see what I mean. So if you have something like the sine of 2x, and you take its derivative, then the chain rule says you get cosine of 2x times 2. So the way I like to think of this is this sine of 2x has been horribly differentiated, right? Someone came along and differentiated sine of 2x. And it's like they whacked it with the differentiation hammer and they turned the sine, of course, into a cosine. So sine of some stuff became cosine of the stuff. But then the chain rule says you have to multiply by the derivative of the stuff. So it's like that extra 2 got splattered out on the ground next to the cosine of 2x. So we come across this cosine of 2x and a 2 laying there beside it, and it's clear that it's been chain ruled, right? That 2 laying out there beside it is the derivative of the 2x, which is inside the cosine. And so what you expect to see when something's been chain ruled is like a function with something inside that's not just an x. In this case, it's 2x. And then the derivative of that something laid out to the side of our function, just laying there, like it's been knocked out to the side and is left there as the remains of the differentiator. So if we were going to go backwards from something like that, right, if we come across the scene of a differentiation and there's cosine of 2x with a 2 laying over there beside it, then we can put those back together, right, by undoing the chain rule, right, that the 2 cosine of 2x should go back to being sine of 2x, okay? And if we write this out, sort of formally the way I have here with u's and x's and things to try to come up with a rule, then you can sort of see how substitution is going to show up when this formally, and we'll do it slowly and carefully and formally with u's representing the 2x's, and we'll see how this falls out. So here we go. Let's start with the problem that we had before, 2 cosine of 2x, and do it slowly and carefully, reconstructing the chain rule the way we would do a more complicated kind of problem, even though this one's pretty easy, right? We know the 2 is going to get drawn back inside the sine of 2x when we undo the chain rule. But if we do this slowly and carefully using this idea of substitution, maybe you can see where all the pieces come from. Here's what I mean. I'm going to substitute u for the 2x. Because remember how the chain rule works? It's like if you have sine of a bunch of stuff, okay, then you do the derivative of the sine, leave the stuff alone, and then multiply by the derivative of the stuff out beside it. That's how this gets a 2 sitting out there in front of the cosine. So what we're going to do is we're going to let u be the stuff. That's the way this is going to work. U will be our stuff. So we can use this rule that the integral of cosine of u should just be sine of u. Like that's our integral rule. So if we let u be our leftover stuff, or our stuff that's inside the function, that's the idea. So here, u should be 2x, okay? But in our integral, we don't just have letters like x and our u, we also have dx's and of course du's. So if u is 2x, then we can use what we know about differentials. Du should be 2 dx's, right? Again, if you like to think of this the other way around, you could say over dx is 2x, and then move the dx to the other side. That's a little bit of abusive notation, but it works with the notation we're using here. So u is equal to 2x, that's our stuff that's inside the cosine. And then the derivative of the 2x should be 2. So du is 2 dx. So then we just substitute what's in that box into the integral. So instead of having 2 cosine of 2x dx, we replace that 2x, again, that's the stuff inside the cosine, with a u. That's fine. And then we replace the 2 and the dx with a du. That's perfect. And now it fits exactly our rule, because I have the integral of cosine of u and a du. That's perfect. There's no extra x's left. There's no muss, no fuss. It's an easy rule that we know how to do. So the integral of cosine of u should be sine of u, of course, plus c. Okay, now the original problem had x's in it, and I've got an answer that has u's in it, so obviously we've got to fix that. But that's easy enough. We know what u is. According to our big box there, u is 2x. So I just replaced that u, the stuff that was inside our original cosine, turn that back into 2x's. So we end up with the sine of 2x plus c. So you may very well be asking yourself, okay, this was really boring, because I could have started with this first integral and solved it. 2 cosine of 2x is just a function that's been horribly chain ruled, right? You look at it and you go, yeah, you've been chain ruled, and I know how to put you back together. You were originally a sine of 2x, and that extra 2 that's sitting out there in front of the cosine comes from the chain rule. I get that. So why do I have to go through all this mess with these u's and du's and stuff? Well, the answer is sometimes it's not quite so obvious how you do it. Sometimes we come across something that's been horribly differentiated and chain ruled, but the derivative of the stuff, or at least the constant, isn't there. Let me show you what I mean. Here's one. We just have the integral of cosine of 2x. So that extra 2 that you would expect from the chain rule isn't there anymore. We just have cosine of stuff. There's no derivative of stuff sitting next to it. So here's where that whole procedure with being really careful with calling our stuff a u and writing down things carefully rides in to save us. So here's what I mean. I'm going to let u equal the stuff inside of cosine. Again, why don't I just call that sine of 2x and be done with it and just integrate it like that? Because that would break the way that the chain rule works, right? When you have a derivative of, say, sine of a bunch of stuff, right? And the stuff's not just an x, right? Like if you had sine of 2x. When you took the derivative, you wouldn't just make it cosine of 2x. You'd have to make it cosine of 2x and then put a 2 out beside it. It's the same thing here. I can't just look at that cosine and turn it into a sine, right? Because that's not how the chain rule works. When I tried to, if I took my answer and took its derivative, I wouldn't get back to what I started because of the chain rule. So, slowly and carefully, I let the u, the stuff inside my cosine, be my 2x, okay? There's my stuff inside the cosine. Now, in order to make this turn into an integral that's all full of u's, I've got to deal with the fact that there's a dx sitting there, not just a cosine of 2x. So I'll deal with that by figuring out how to turn that dx into some du's, right? So what's the derivative of 2x? Well, just 2. So if u is 2x, when I take the derivative, du would be 2 dx's. Again, this is just taking derivatives and writing things down in differential form. Okay, so in my original integral, I have a cosine of 2x, which that'll be easy enough to deal with because I'll make that cosine of u. Okay? The u was equal to 2x, and slide that in there, not a problem. What about the dx? See, I got to somehow turn that into a du, but du is equal to 2 dx's, and I'm short a 2. See, there's no 2 there. So let's do it this way. Let's take that dx and solve for it in that equation. In other words, take the 2 to the other side. And that would tell us that the dx, which is what I have, is equal to 1/2 du. Then I can substitute that in. So my cosine of 2x will become cosine of u, because the u is 2x. That was the stuff inside the cosine to begin with. Easy, easy, easy. what about the dx that's sitting there in my original integral? Well, according to the little calculation we just did, dx is 1/2 times du. So I just replace that dx, substitute in for that dx, 1/2 du. And of course, that 1/2 is a constant. So I could just write it on the outside of the integral, right? A constant like that is never a problem, right? I can move that in and out of the integral. That's not what's giving me difficulty when I try to integrate something. So I have the 1/2 still floating around, and then a cosine of u. Well, that's easy. I know how to integrate a cosine of u, a cosine of just one letter, right? And then if the thing sitting next to it is d of that same letter, in other words, cosine of u du, I know how to integrate that. That's just sine of u, right? And the 1/2 that was sitting out front is still sitting out front. And finally now, I substitute in 2x back for the u, because my original problem had x's in it, so I can't leave my problem with u's. I need to go back to make sure my answer has x's in it. So don't forget to go back to x's in your final answer. Now, if you think about what the problem we did, 2 minutes ago, then this is really pretty obvious, right? When I looked at the integral of 2 cosine of x, 2 cosine of 2x, the first example we did, then I got sine of 2x. Here I don't have that 2, I only have half as much. So obviously the answer should be half as much. It should be 1/2 sine of 2x. And if you compare those two examples, you think, well, maybe that's just obvious that this problem we're working on the screen now is half of the problem I did before. Right? And that's true. That's exactly true. That's exactly how all of this works. But going through this machinery, letting u equal the stuff that's inside another function, then working out that du has to be whatever it is, and in this case we solved for dx, that gives us a machinery that will always work, that even if we get a very complicated kind of problem, and we will have some very complicated kinds of problems, that we can work our way step by step through it and keep everything nice and organized, and use that to undo this chain rule effect. Okay, so I would be remiss in my duties if I didn't stop and give you a different way to work this problem. So here's what I'm going to show you. I'm going to show you an example. In fact, it's a different slide here that we're going to go through. And this is a slide that actually appears in the slides we use in Calculus 2. So this is a review slide in the section of review material that we would do in Calculus 2. And it's exactly the same problem. But I'm going to work it slightly differently. And the reason is, in Calculus 2, everybody already knows how to do substitution, or they should. And doing substitution is something we're going to have to do really fast in Calculus 2. I mean, for now, doing a substitution problem is the whole problem. In Calculus 2, doing a substitution may be one of the 3 steps in a 15-step problem. Okay, so we've got to be able to do this quickly and get on with it, right? So here's how I would explain this in Calculus 2. And if you like this way of thinking about it, then feel free to do it now. If this makes you uncomfortable, then stick with what we showed you on the last page. So here's what I'm going to do. I have cosine of a bunch of stuff. The stuff is not just an x, it's a 2x. So this is an obvious example of where I'll need to do u substitution. So I'll let u be my 2x. Then obviously my du will have to be 2dx again, just like on the last page. The thing that's a little different now is I want to think about this a little differently. Instead of solving for dx and saying that dx is 1/2 du, here's another way of thinking about this problem, which is completely equivalent. I'm not doing anything that's really any different, right? But it may go a little quicker for you, or it may not. And if it doesn't, then do it whichever way works best for you. So here's what I'm going to do. I'm going to look at this and go, if there were a 2, and this is sort of a brown 2, so the color coding I hope may help. If there were a brown 2 sitting next to my dx in my original problem, then I would just erase the 2, erase the dx, and replace it with a red du. Okay? But I don't have a brown 2 sitting next to my dx. So here's what I'm going to do. I'm going to cheat. I'm going to put 1 there. I'm going to write a 2 next to the dx. Okay? So then it looks like it's been chain ruled, right? It looks like the very first problem that we did. So written this way, I could take the brown 2 and the dx and replace it with my red du. Okay? And again, just substituting the red du in place of the brown 2 and the dx, and we're good to go. Now, if I just start sticking 2's in there wherever I please, right, then of course I'm changing the problem, right? I can't, it's not legal to just go in and stick a 2 in there just because I want one. So if I do that, what I have to do is balance it out, right? So there's no other side of the equation here because there is no equation. But what there is multiplied by a 2, I would cancel that out and in effect not done anything if I also divided by 2. So if I write a brown 2 next to the dx, I could write a brown 1/2 outside the integral. And of course, I can take that number outside the integral, move it inside the integral if I wanted to, and multiply it by the 2 and get back to what I started. Now, I'm not going to do that because I need that brown 2 there so I can turn it into a du. But you see what's happened, right? I haven't changed the problem if I put a brown 2 next to the dx and also a brown 1/2 on the outside. Those would cancel themselves and go back to what we started with. But I'm not going to cancel them. I'm going to substitute them. I'm going to take the 2 and the dx and turn that into a red du. I'm going to take the stuff inside the cosine, the 2x. That was originally what I used for u. So I replaced that 2x with a u. And now the brown 1/2 that was outside is still hanging around outside. That's perfectly fine. That gets me 1/2 times a cosine of u du. And I know how to integrate that. Cosine of u should be sine of u plus c when I integrate that. And then I turn those u's back into x's, so I stick the 2x back inside the sine of u, and that becomes now 1/2 sine 2x plus c. So exactly the same answer we had before, and it's almost exactly the same process we had before. But if you were doing this in your head, and when I show this slide in Calculus 2, I will tell people in Calculus 2, you need to be able to go from the top line to the bottom line in your head because you'll have done 100 or more of these problems. So that's one reason why this section is so important in Calculus 1, so that you get really good at this, because in Cal 2, it's doing this constantly, over and over and over again, as a minuscule part of a much bigger problem. Okay, so we definitely need some more examples. Let's do one with a square root. So if we look at this guy, this is a square root, and there's some stuff inside the square root. It's not just a square root of x. It's square root of x squared plus 3. So that stuff inside the square root, well, looks like stuff from the chain rule. What's the derivative of that stuff? 2x. Okay? Now I've got an x outside. Okay? I don't have the 2, but as we saw before, that's not a problem. Right? I can add 2's, I can add a half. I can't fix x's. If I didn't have that x there, I'd be stuck. In fact, that'd be a Calculus 2 problem, and there are ways to do this that you would learn in Calculus 2. But without that x on the outside, I'd be stuck. I can't fake an x, right? Because again, that would break, if you stop and think about it, that'd break the way the product rule for derivatives works. But I can fix the fact that there isn't a 2 there. So constants we can fix, variables we can't. Okay, so let me show you what I mean. So let's go through the whole procedure of letting u equal that stuff inside the square root. So u is all the stuff, the x squared plus 3. The derivative of u would be 2x plus 0, so I won't bother to write that down. So du would be 2x dx. Okay? Awesome. That's exactly what I need, because I have a dx that I've got to deal with. In fact, I've got an x that I'm going to have to deal with. So if I were to solve for my x dx, right, that tells me that x times dx, which is what's in my integral, is equal to 1/2 du. So I can then take the original integral that I had, replace the stuff in the square root with u, because that's what u is, then take the x and the dx and replace that with 1/2 of a du. So if this is a little confusing, and it probably is the first time you see it, pause for a second and just stare at the screen for a second. Look at every piece of those, of both of those integrals on the bottom line, and make sure you understand where each piece comes from, what happened, right? That square root of x squared plus 3, well, that's a square root of some stuff. And the whole point is this thing's been chain ruled that x squared plus 3 is my stuff inside the square root, inside my function. So x squared plus 3 is my u. I originally had a square root of x squared plus 3. That's why I have a square root of u now in the new integral on the right-hand side. Originally, I had an x and the dx, and I need to somehow turn that into something that'll give me du's. So I'll have an integral with u's in it and also a du at the end. So they've got to have the same letter all the way through. Well, I do a little algebra on the line above that, and x times dx is 1/2 of du. So I replace the x and the dx with 1/2 of du. And again, if that still seems a little weird and freaky, pause it and reread it until it starts to get clearer. Okay? All right, so now how would I integrate something like this? Well, let me take the 2, or the 1/2, stick it out in front so it's out of my way. How do you integrate a square root? You make it u to the 1/2 power. Now it's a u raised to a power, so it's really easy because it's just the power rule, right? I take that u to the 1/2, I add 1, that would give me 3/2. So I have u to the 3/2 divided by 3/2. Or if you don't want to write divided by 3/2, you could flip it and multiply it and make it multiplied by 2/3, either way. That 1/2 that was outside the integral is also still outside, or being multiplied by, the rest of the stuff that I get when I integrate. So I finally end up with that 1/2 times 2/3, if I flipped it and multiplied, times u to the 3/2 plus c. And then finally, I can turn all those u's back into x's, replace the u with x squared plus 3. Now, it's probably worth pausing and reworking, right? One of these, maybe the first several times you do this. So at the end of the video here, pause the screen and take the derivative of the answer that we got. You'll need the chain rule. And if you take the derivative of this, you'll have, some stuff raised to a power. The x squared plus 3 is my stuff. So I'll take my x squared plus 3 as my stuff. I have stuff raised to a power, so the derivative would be stuff raised to that same power minus 1, and I multiply the power down in front, and then do the chain rule and pick myself up an extra 2x. When you do that and sort of work your way backwards, you'll see that the chain rule gets us right back to the original integral that we started with.